So in this video we will learn what is the Lagrange multiplier method for finding maxima and minima of a constant function and how it works. But before that, let us first see what is a constant function. What is a constant function? Now let us take this example. We are given a function of two variables given by the rule f is equals to 3x plus 4y. Now it's a polynomial function and its domain is the entire xy plane. So this one is x-axis and y-axis, x-axis, y-axis. So the domain of this function is the entire xy plane, So any point xy is a candidate at which this function could have a maximum value or a minimum value. Now let us take another example. We are taking the same function f, a function of xy given by the rule 3x plus 4y, with this restriction that xy can take only those values which lie along this unit circle as x squared plus y squared is equals to 1. Now the domain of this function has been restricted. Now xy cannot take any value from this xy plane, but only those values which lie along these unit circle. So we have put a restriction on the function, okay, and this restriction we call a constraint. So this circle act as a constraint to the function, and we say that this function is a constant function. We already know how to find a maxima or a minima of a function which is not constant. Here we will learn how to find maxima minima of a constant function. So next we learn what is the method of Lagrange multipliers, and to understand it we take our same example. Our function is given by the rule 3x plus 4y subjected to the constraint x squared plus y squared equals to 1. That is a circle, unit circle, and we have to find maximum and the minimum value of this function f subjected to the condition that xy lay on the unit circle only. Fine. Now let us try to understand this problem with the help of the geometry. Now the geometrical meaning of this function is it's a surface which is a plane z equals to 3x plus 4y, okay, and its label curves are the curves of projection of this plane in the xy plane. So they are given by this equation 3x plus 4y equal to c. They are the label curves. So geometrical meaning of the function is a surface, and these are the label curves of the given surface. Now what are these label curves? These are simply for different values of c. They are simply a set of parallel straight lines, a family of straight lines. So let us draw these straight lines in xy plane. So this one is x-axis and we have y-axis. Suppose we take c equals to 0, so we will get a straight line passing through origin, So this is the label curve corresponding to c equals to 0. Similarly, for different values of c, we will take straight lines which will be parallel to this straight line. So we draw other parallel straight lines here. Another parallel line here. For different values of c, a straight line here. Now as we know that this function is a constant function, xy can take only those values which lie along the unit circle. So let us draw the unit circle here. So suppose this one is distance 1, and so let us draw the unit circle here. We got so this is our unit circle, x square plus y square equal to 1, and we have to find maxima minima of the function f equal to 3x plus 4y at only those points which lie along the circle, right? Okay, so these are the possible points which are common to these label curves as well as the circle. So this point, it could have a maxima minima at this point, this point, this one, this one, this one, this one, this one, this one. And from the diagram we can see that as we go further away from the origin, okay, the value of the this function increases, and this is the point which is common to the curve as well as the constraint. And this point, the function is having the maximum value, and just on the opposite side, this is the point where the function will have a minimum value. Now consider this point. Now at this point of maximum value of the function and minimum value of the function subjected to the constraint, we can see that the normal vector to the circle, as well as the normal vector to the label curve c equals to c2, they are in the same direction. And we know that the normal vector to any curve is given by gradient. So normal vector to this label curve c equal to c2 is given by gradient of f is equals to, they are in the same direction, is equal to some multiplier, some lambda multiplied by, this is gradient of g, where g represents the function x squared plus y squared minus 1. And the same holds at the other end, the other extreme, where the function is having a minimum value. Again the normal vector again the normal vector to the constraint, that is the circle, as well as the normal vector to the label curve c equal to c2 dash, they are in the same direction, So this condition again holds at the point of minima. And this is the basic idea behind the Lagrange multiplier method. At the point of maxima and minima, the gradient of the function is equal to some lambda times the gradient of the function that we obtained from the constraint. This lambda is an unknown parameter, and we call is a Lagrange multiplier. Now if we simplify this equation, we know gradient of f is del f by del x I vector plus del f by del y j vector is equal to lambda times gradient of g delta del g over del x I vector multiplied by plus del z over del y j vector. And if we compare the left hand side and the right hand side of this equation, we get del f over del x equals to lambda times del z by del x, first equation. Second equation is del f by del y equals to lambda times del z by del y, the second equation. And the third equation that involves in the Lagrange multiplier method is the equation of the constraint, and in this case x squared plus y squared equals to 1, the equation of the constraint. So how does the Lagrange multiplier method works? At the points of maxima and minima, this equation holds. Gradient f is equal to lambda gradient of g, where f is the function at which we have to find the maxima and minima, and this equation is actually a couple of equations given by equation number 1 and equation number 2. Now we have to find maxima, the point at which the function has a maxima or minima. So we need x, y values. We get these points of maxima and minima by solving to equation number 1, 2 and 3. Why we are having 3 equations? Because we have 3 unknowns, x variable, y variable, okay, which will give us the point, and the third unknown parameter, that is lambda. So by solving these equation number 1, 2 and 3 simultaneously, we get the points at which the function could have a maxima or a minima. Now we remember that Lagrange method does not give the nature of the point, right? It only says that at these points the function will have a maxima or a minima. It does not tells us that it's precisely it will be a point of maxima and this will be a point of minima. To decide whether it's a maxima or minima, we apply our previous knowledge of mathematics. So in this example, we have to find the greatest and smallest values that the function f of two variables x and y given by 3x plus 4y takes on the unit circle x squared plus y squared equals to 1, and we'll solve this problem using Lagrange multiplier method. So this is our solution. We have to find the maximum and minimum value of the given function. So our function is f equals to 3x plus 4y. This is the function, and a constraint is the unit circle x. So our function g function is a function of x comma y equals to x squared plus y squared minus 1, which we have obtained from the constraint. Now the Lagrange multiplier method says that at the point of maxima and minima, so at the point where the function could have a maxima or a minima, gradient of f is equals to lambda times gradient of g. So lambda is a multiplier, that's why the name Lagrange multiplier method. Okay, and this equation simply boils down to in its component form as del f by del x, partial derivative of f with respect to x equals to lambda partial derivative of g with respect to x, our first equation. Second equation will be del f by del y is equals to lambda times partial derivative of g with respect to y, second equation. And the third equation that will help us is the equation of the constant, that is x squared plus y squared equals to 1, and this is our equation number 3. By solving these 3 equations, we will get the points at which the function could have a maxima or a minima, right? So partial derivative of f with respect to x, we will use this function. We have partial derivative of f with respect to x, y will be treated as a constant, so the value comes out to be 3, and partial derivative of f with respect to y, it will be 4. Similarly, partial derivative of g with respect to x, it will be 2x, and partial derivative of g with respect to y, it will be 2y. Let us put all these values in equation number 1 and 2. So equation number 1 implies we have del f by del x 3 is equals to lambda times 2x, and equation number 2 implies 4 is equal to lambda times 2y. And of course our third equation is x squared plus y squared equal to 1. Now from this point onwards there are two ways that we could follow, right? First way is like we find the value of x in terms of lambda, we find the value of y in terms of lambda, we put those x and y values in equation number 3. By solving 3 we get the value of lambda and we put it in equation number 1 and 2 to obtain x and y. The another way is we eliminate lambda with the help of these two equations. Here I'm opting for the second method, right? So we eliminate lambda from these two equations by simply dividing these two equations. So by dividing, so we are dividing equation number 1 here by equation number 2, and it comes out to be 3 over 4 is equal to 2 lambda x over 2 lambda y. 2 lambda and 2 lambda cancels out and we simply get y is equals to 4x over 3. Now we have already used equation number 1 and 2. We have not still used the equation number 3. We put the value of y into equation number 3 to obtain the value of x. So putting y equal to 4x over 3 in equation number 3, we get x squared plus 4x over 3 whole squared is equals to 1. X squared comes out to be common. This is 1 plus 16 over 9 is equals to 1. And simplifying it, we get 9 plus 16, 25 over 9. It goes on the right hand side and we get x squared as 9 over 25, and this implies the values of x are positive 3 over 5 and negative 2 possible values of x. We put the value of x equals to plus minus 5 in, we put this value of x into this equation y equal to 4x over 3. So when x is equals to 3 over 5, we put 3 over 5 here, 3 and 3 cancels out, we get y equals to 4 over 5, right? One point of maxima minima is this, and the another one is if we put x equals to minus 3 over 5, we will get y equals to minus 4 over 5. So another set of points at which the function could have a maxima and minima. So our points of maxima, minima possible. So using Lagrange multiplier, we have obtained the points at which the function could have a maxima or minima. First one point is 3 over 5 comma 4 over 5, and the another point is minus 3 over 5 comma minus 4 over 5. Possible points where the function 3x plus 4y subjected to this constraint could have a maximum value or a minimum value. As discussed earlier, Lagrange method does not give the nature of these points of maxima minima. It cannot tell us that whether there will be a maxima or a minima at this point, and we use our previous knowledge of mathematics to find the nature of these points. Okay, so in this case it is very simple, right? Let us to decide the nature of the point, let us find the values of the function at these points, right? So f at 3 over 5 comma 4 over 5 is equal to 3 multiplied by 3 over 5 plus 4 multiplied by 4 over 5. This is equals to 9 over 5 plus 16 over 5. This comes out to be 25 over 5. This is equal to 5. Okay. And f value of function at the point minus 3 over 5 comma minus 3 over 5. This is equal to this will be 3 multiplied by minus 3 over 5 plus this point is minus 4 by 5, this coordinate, and 4 multiplied by minus 4 by 5, which on simplification will give us minus 5. So we can see that since 5 is greater than minus 5, so the function will have a maxima at the point 3 over 5 comma 4 over 5. This is point of maxima, and the second one is the point of minima. So the given function will have a maxima, the greatest value at point 3 over 5 comma 4 over 5, and the maximum value is the greatest value is 5, and it will have a minima at point minus 3 over 5 comma minus 4 over 5, and the least value, the least value is minus 5. Now we can see this problem with the help of geometry, which we have discussed earlier. So this one is the point where the function is having the maximum value, and this point is 3 over 5 comma 4 over 5, the first quadrant, and this is the point where the function is having the minimum value, and this point is minus 3 over 5 comma minus 4 over 5. Thank you.